In this video, we're going to discuss titrations, which is something we've covered briefly already this year, but now we're going to get into more depth with our knowledge of buffers and pH and pOH and Ka values and whatnot. So a titration is an experimental technique, okay, where you complete a neutralization reaction. Okay. So since it's a neutralization reaction, that means we're either adding an acid to a base or we're adding a base to an acid. Okay? And the power of this, one of the main reasons we usually conduct titrations, the main purpose is to determine the concentration of an unknown acid or base. So usually the way this works is we have a beaker, we have our burette up above it, and we've done this before, and in the burette there is either a base or acid where you know the concentration, it's known concentration, and in a beaker down below, okay, you have the opposite. So if you have a base in the burette, you would have an acid in here. Or if you have an acid in the burette, you would have a base in here. And you don't know the concentration. And now with our knowledge of stoichiometry and a few other manipulations, we'll be able to figure out the concentration, the pH, and a bunch of other information. So the first main type of titration that's done is the most common type. And that's when we take a strong base and add it to a strong acid. So you got to know your strong acids, all 6 of them. Strong bases, the most common ones that we use are sodium hydroxide, NaOH, or lithium hydroxide, or potassium hydroxide, a group 1 metal with OH. Okay? What we do is we add, what we're going to do in this class now is we're going to take our acid in a beaker, okay, and we're going to add our base drop by drop into it. And when we do that, we're going to use a pH meter, okay? It's going to be a digital tool that's going to tell us what the pH of the solution is. So over time, as we add more and more base, we're going to record the pH. When we plot that data and we put the volume of NaOH or base added on the x-axis and the pH on the y-axis, we get something that is called a titration curve. Titration curve. Titration curves, you need to know, always have pH on the y-axis, and they always have volume on the x-axis. It might be volume of base, or it could be volume of acid, depending on what's in your beaker when you're doing your titration. Okay. This is an example of a titration curve when you mix a strong base with a strong acid. There's a few key things you need to know. The first one is this point right here, which is in the middle of the vertical line. The middle of the vertical line, going up and down, is called the equivalence point. Okay? And if we break down that word equivalence, it sounds like equal. Something is equal at the equivalence point. What is equal at the equivalence point? This is when your moles of H plus of acid equal your moles of OH minus. So if you have 2 moles of H plus, you've added 2 moles of OH minus. Or if you've added 4 moles of H plus, you've added 4 moles of OH minus. They have to be equal. And the reason for that is because if you take 1 mole of H plus 1 mole of OH minus, you make water, H2O. Why is that special? Well, for adding a strong base to a strong acid, the equivalence point is always going to have a pH equal to 7. So that's something you need to know. When you add a strong base to a strong acid, the pH at the equivalence point is equal to 7. The other main thing you need to know is the definition of an equivalence point. That's when the moles of H plus equal the moles of OH minus. How could we figure out the moles of H plus? Well, if you look at the equivalence point and you drop this down here, we get the volume of OH. In this case, it looks like it's about 25 milliliters. So what we could do is if we know that we added 25 milliliters from our burette, 25 milliliters, that's the same as 0.025 liters, times the concentration, okay, of NaOH. Let's just say it was 1 molar NaOH. I made that up. Then it would be 1 mole per 1 liter. So you would have 0.025 moles of hydroxide, OH minus, that were added. What's powerful there? Well, you know, therefore, at the equivalence point, you must also have 0.025 moles of H plus. Because at the equivalence point, the moles of H plus and the moles of OH minus are equal. That's what gives you the neutral pH. So we'll do calculations with calculating moles and determining pH and everything, but that's when a strong base is added to a strong acid. What if you add a strong base to a weak acid? Now things are a little bit different. This is still a titration curve because we have pH on the y-axis and volume on the x-axis. But you might notice something a little bit different. This line right here is a lot longer, okay? And the pH in this region is not changing that much. It's a very small change in pH, even though you're adding, let's look, from 5 to about 25, even though you're adding 25 milliliters of base. So we're adding all this base, but the pH isn't really changing that much. So what must be going on? Well, we know that solutions that don't change their pH very much are buffers. So this is the buffering region of this titration curve. I know it's buffering because it's kind of a longer line, and I have a weak acid present. There's a weak acid in the flask. We still have this special point here. That's still our equivalence point. Okay? Equivalence point, where moles of H plus equal moles of OH minus. But there's a new term that we need to know for this point, which I'm going to label in green. Boom. Okay? If you notice, the volume here is about 15. The volume here is about, it's a little bit off, about 30. This is half the volume. This particular point is called the half equivalence point because you've added half the moles of base that are needed because you've added half the volume. But also, the special thing about the half equivalence point, which is also sometimes called the midpoint, okay, is that the concentration of the acid is equal to the concentration of the conjugate base. These concentrations are equal at the half equivalence point. And we know from the Henderson-Hasselbalch equation, if this is true, therefore, the pH equals the pKa. So the next thing you need to know is if a weak acid is getting titrated, the pH right here at the half equivalence point, that is equal to the pKa of the acid. So that's another way you can figure out what the acid is. If you get the half equivalence point, okay, you know the pKa, and the pKa is unique to any acid, so you could figure out what the acid is by looking at a table of known Kas. So big things to know from here, from this titration curve, you need to understand that this is the buffering region, where the pH isn't changing very much. The halfway point, called the midpoint or the half equivalence point, is when the pH equals the pKa because the concentration of the conjugate acid and conjugate base and weak acid are equal. And the equivalence point still is true. The last thing you need to notice is look at the pH. The pH at the equivalence point is greater than 7. That's because you will have more conjugate base present because all of the acid will have been neutralized. So when a strong base is added to a weak acid, the pH will be greater than 7. Again, because there's more conjugate base, there will be more conjugate base present because all the acid has been neutralized. Another example is the same type of thing that's an inverse. Here we have pH, but volume of acid added. So that means that in your beaker, okay, you started with base. So how can we tell that from the titration curve? Well, we know bases have pHs of greater than 7. So the starting pH here is much greater than 7. So since this is a strong acid to a strong base, the same things apply. This point right here is the equivalence point, where the moles of H plus equal moles of OH minus. Since it's strong to strong, pH is equal to 7. And then we can see that this volume right here would represent the volume of acid needed to determine the concentration of the base. So you got to recognize a curve like this means that you start with a base in the flask and you're adding an acid to it, whereas a curve like this means you have an acid in the flask and you're adding base. The last type of titration curve we need to recognize are for curves for polyprotic acids. Remember, these are acids with more than one hydrogen present. So an example could be H2SO4 or H3PO4, anything that has multiple hydrogens present. How do I know this is the titration curve for a polyprotic acid? Well, the number of bumps, okay, is equal to the number of hydrogens in the compound. So here, how many bumps do I have? Well, I have one bump here going up, then I have a second bump right here. So since I have two bumps, this acid would have two hydrogens. It'd be H2 something, okay, whatever that is. Same rules apply, okay? This is still your equivalence point, but now it's your first equivalence point, okay? Equivalence point number 1, where the moles of H plus equal moles of OH minus. And then here, this is another equivalence point, but for the titration of the second acid. You still have the midpoint, or the half equivalence point. What's special here, as the pH equals the pKa of an acid losing its first hydrogen, whereas here, at the second equivalence point, the half equivalence point, this is where the pKa of the second acid equals the pH. Okay? Why is that true? Well, let's just take an example of a polyprotic acid. You know, H2SO4 can dissociate into H plus and HSO4 minus. This can then also dissociate to make H plus SO4 2 minus. Okay? So technically it should be 2H plus. So the pKa of this acid would be equal to the pH at the first equivalent point, whereas the pKa of this acid would be the pH at this equivalence point. So we need to know how to recognize these diagrams and then use our knowledge of pH, pOH, and whatnot to do problems involving titration curves for polyprotic acids, for strong acids to strong bases to weak acids, strong bases to strong acids.